We are going to reach out to one more idea about what could have caused the drawdown of CO2 during the last ice age. There is obviously evidence that the change in atmospheric PCO2 as measured in the bubbles in the ice core and temperature changes do correlate. So here are two examples. This is the magnesium derived Pacific temperature showing a few spots of warm and cold temperature anomalies, and this is showing PCO2 from Taylor Dome. So you can see that the warm temperatures correspond to higher PCO2 and cold temperatures correspond to lower PCO2 and so on. And even during the recent little ice age that occurred over about the end of the medieval warm period, 1200s, 1300s to the beginning of the Industrial Revolution essentially. And there are reasons. It started with the increased volcanic activity that could have ended the medieval warm period, which led to the Vikings colonizing Greenland and so on. And then there were several solar minima in this period as well. As we know, the sunspots on the sunspots have influence on solar activity. So more the sunspots, less the energy coming out, because around the sunspots, which are not in the magnetic field, there is higher radiation. So if there is a minima in solar activity, then radiation is maximum. So if you radiation is maximum, if sunspots are reduced, solar radiation is reduced. If sunspots are more radiation, because around the sunspots you get more sunlight. They're called plage. Okay, so solar activity minima correspond to minima in radiation, which correspond to the little ice age. Boom, boom. Okay, so that corresponds to a reduction in PCO2 as well. So this idea is already accepted. But what circulation changes have been invoked for explaining the drawdown of CO2? If we look at this nice figure from Lynn Talley's book and her course at Scripps, we can see that the dense water produced in the Southern Ocean of Antarctica, there are the ice shelves which release brine and cause density to increase, katabatic winds increase heat loss and sea ice formation. There are polynyas, which are holes in the ice, which create lots of energy loss from the ocean to the atmosphere and cool the water as well. All said, you have Antarctic bottom water, the heaviest water rushing down to the bottom, and in the North Atlantic, you have the North Atlantic deep water formation, which is flowing south, and it's riding on top of the Antarctic bottom water, and the Antarctica is also producing these Antarctic intermediate waters, and you have these wind forcing where Antarctic circumpolar current, the westerlies and easterlies together are pulling up the water, so you have the North Atlantic deep waters being upwelled to the surface here, and so on. So during the ice age, as we mentioned before, the North Atlantic probably would have been covered with land glaciers, of course, but sea ice, which would have probably reduced, and there is evidence for this. The deep water formation, which means the saltier, colder Antarctic bottom water would have created what is called a salt blob in the deeper ocean, and this would have resulted potentially in alkalinity changes and lock-up CO2. This is the idea that was proposed by Jess Adkins and collaborators, and people have looked for this cold blob, salty blob, and it turns out that such a salty blob indeed was present, and the models can reproduce it given the forcing of the last glacial maximum and so on and so forth. And then you have to go through the arguments to see whether such a blob could have sequestered 80 to 100 ppm of CO2 in the ocean. Okay, Just like we are looking for consistency checks for each idea. For example, we know that the CO2 drawdown during the Ice Age was 80 to 100 ppm, but then you have to look for isotopic evidence of whether that CO2 in the bubbles in the ice cores was lighter or heavier. That would tell you whether it came from increased biological activity or whether it was done with inorganic carbon cycle in the ocean and so on. So similarly here, for a cold blob to hide away that much CO2 that we are looking for, 80 to 100 ppm, we have to go back to all the physics. For example, in the current climate, this is the chlorophyll concentration from satellite data in milligrams per meter cube for summer months, boreal summer months, July, August, September, and boreal winter months, January, February, March. So obviously there is high production in polar regions in the spring, summer months. You can see here and here. As sunlight is available, mixing is deeper, nutrients are available. Spring production is high, but there is also summer production, especially in the coastal shelf areas in the Mediterranean Sea and so on. And you also see what we called before as the iron deficit regions, where you see that nitrate is high, chlorophyll is high but not using up all the nitrate. So these are called high nitrate, low chlorophyll areas, or HNLC regions. You can see that there is chlorophyll high here but not nutrient, no nitrate. So this, and it's true also for the Southern Ocean. There is high productivity in the summer. Spring is much higher, of course, and still you have incredibly high nitrate concentrations in both seasons, because again there is iron deficiency. So to create this salt blob and to hide away so much carbon, you have to have a consistent signature in the relation between carbon and nutrients. In general, it turns out that regions where there is low chlorophyll or low biological activity, there is low nutrients as well. And in the regions where there is high biological activity and high nutrients, which are obviously used up when there is high biological activity, then there is also high CO2, which is called metabolic CO2. So the deep ocean, as we saw, has high nutrients. Surface waters typically have low nutrients because biological activity uses up, but the nutrients are typically associated with CO2 because of the photosynthesis and so on, compared to low productivity regions. Okay, long story short, you also have to then combine it with the way water chemistry works. We know that seawater takes up CO2, but it's not kept as CO2. It's all moved into HCO3 bicarbonate and carbonate, right? Carbonate is much higher than CO2 in the water, and then there is calcium carbonate. So if you wanted to lock up lots of CO2 in a blob of water, you would have to have taken it as HCO3 minus, which is not easy because of these buffering reactions. And when you have HCO3 minus, you have pH changes which would drive carbonate pH carbonate pH stat as well. So you would melt or you'll dissolve calcium carbonate and so on. So you will have to find not only the salt blob but all the other nutrient and calcium carbonate signatures that are consistent with hiding so much CO2 in water, which is already very difficult. And even if you manage to somehow create a huge enough blob of salt water that can have, let's say, 10% more CO2 than normal, and somehow manage to add enough CO2 in the water, you will have to see what kind of CO2 blob it creates in the atmosphere associated with that drawdown in the blob. And it turns out, essentially, I'm not probably doing as good a job as the book does in explaining all these details, so you should definitely read the book. But I'm just trying to drive the point that when you check all the evidences together, it is now clear that a salt blob did exist, but there is no clear evidence that this salt blob could explain 80 to 100 ppm change in CO2. At best, it could have explained 20 ppm or so. So it could have been a key player, but not the complete story. Okay, so circulation changes. There are other ideas used as well in terms of movement of these fronts that exist between the subtropics and the polar regions and so on, subpolar and subtropical fronts. And moving them also changes these circulations. There is a faster cycle here, a slower cycle here, and so on. So there are ideas based on those as well. But the main message would be that circulation changes are still not able to explain the kind of CO2 change that we are looking for in going from the ice age to the deglaciation of 80 to 100 ppm. Okay, as I said again, read the book for the nice intricate details that David Archer does a good job in explaining. But there are still papers being written about the nutrient levels in the Southern Ocean at that time, and there seems to be evidence for drawdown of nutrients in the surface during the ice age, which would correspond to a stronger biological pump. And the high nitrate, low chlorophyll in the Southern Ocean and the iron deficiency is also consistent with the idea that increased dust during the glacial times may have driven this stronger biological pump. But we still come back to the same thing. Would that explain 80 to 100 ppm change from the interglacial to glacial? It doesn't seem so. So now we'll test one more idea called the ocean pH changes and whether they can explain this large change in CO2 from glacial to interglacial. And obviously that doesn't fully explain the story either.